Good afternoon. Hello, Mr. Gaur.
Hello. Good morning, Mubin. How are you?
I'm fine. Thank you so much.
I think let's begin now. I don't
Yes,
see
please do.
anyone. All right. So I hope you can see this. So now let's move on. Now, if you want, I want to show you the power of a spreadsheet. And if you wish, it's up to you. You can also open your laptop and work along on Excel if you want. Otherwise, I will just show you a demo.
Please show.
Okay.
Please show the
So
demo and share
yeah.
it.
So you can just have a look. So this is my Excel sheet. So I'm going to do a Fibonacci exploration. And is the screen visible to you? Is it
Yes.
okay? Yeah. So what I've done, I'll show this again to you. I'm sure if you use Excel, you know how to quickly populate these numbers. You don't have to type
Yes.
all of them. Okay. And this is what we meant when we started our presentation, like trivial calculations, the technology does. You don't have to fill in. So for the Fibonacci sequence, I have typed the first two with the red color. You can see 1, 1. Okay. Next, what I do, I just add up. Okay. So I add B3 plus B2. Okay. And my answer is 2. And then what you do, this is the good thing about technology. In the corner, right bottom corner, there is a cross. I just double click it and it populates the entire column right up to 50 with the Fibonacci numbers. Can you see this?
Okay.
Okay. So this is one. And here also you can do some prediction with students. You can say, okay, don't look down, predict how many digits would be there. Okay. In the final answer. So for instance, I don't know how many are there. There are about 9 or 10 digits on the 50th. So this is one. Also using this just to see the rate of growth, how fast this is growing. You can just make a quick graph here. You can highlight the whole column and then insert a line graph here. So you can see on your page, I will just make this bigger if you wish. So you can see how fast it grows after, I think, the 83rd or 94th point. Can you see it shoots up? So this is, again, the Excel is doing this for you. Okay. And now
it's like exponential increasing, right?
It looks like an exponent. Exactly. It's really shoots up. Can you see the Fibonacci series? And then the students can experiment and play here. For example, if I go down, okay, let's go to this next part. Now here, what I'm doing is I'm taking one answer of the Fibonacci sequence and dividing it by the previous one. So I start from the second one because the initial one is 1 only. There's nothing before that. Okay. So here I will do this number B3 divided by B2. Okay. And I get a 1, and I do the same. I just double click on this and it will populate this with all the ratios. You can see now here you see there's something interesting.
But how does the Excel calculate automatically? Like
yeah, it looks at the first pattern, what you did there, and populate. That's why I'm saying it, the technology. This is where it lightens. You know, just imagine sitting and doing all these calculations. I would have lost, my motivation would have gone down, and I was just doing useless calculations. Excel has an inbuilt algorithm. Okay, so it recognizes the pattern I set here, which is B3 by B2. So it'll, for every cell, if I click here, you will see it'll take B11 divided by B10. On top, you can see here. Okay, so it does this for every cell. Okay, so it's saving you the calculation. Now, if you observe this table where I've divided one Fibonacci number by the previous one, in the initial you have 1, 2, this, but you see something strange happens. After a while, it stabilizes. Can you see? It's the same number. So I will just put this in red. For example, this one. So it's 1.6180, whatever. It's up to you how many decimal places you want. You can increase this also. Now here, you can see now, if you are aware, this is the golden ratio. Okay. Now the thing is, it's the golden ratio. Now the thing is, the students can experiment like this. In the Fibonacci sequence, we are starting with 1, 1, right? You ask them, okay, start with any number you want. So why don't you give me a number? You give me some number instead of 1, any other number.
21, for example.
Okay, 21. And below, you give me another number, different number.
15.
15. Okay. So the sequence changes, but look at this one, the ratios. Okay, you will see, interestingly, the ratio still remains 1.6180. I'm just giving you an example how, like, you can do an IA exploration on this or any math explorer. Okay, it's interesting. You play around with this. You can keep changing the first two seeded numbers, these ones. Okay, maybe I can make it a smaller one. Let's say 3, and let's make this 7. Okay. Even then, you see it tends to 1.618039. So this is pretty interesting. Okay, these are the things you can do with technology. Had you done
like the ratio remains is it like ratio remains the same? If we choose the smaller the number, the ratio becomes constant earlier.
Yeah, good. So exactly, now you are looking at some things. You can see some patterns, right? Depending on how you seed the numbers. So exactly. So that's my whole point. So we started with 1, 1, which is the Fibonacci, of course. Okay, and then we can also graph this one, for instance, this one. And if I make a line graph again for this, so you can see how this goes. Okay, this is the ratio sequence. Okay, so the interesting thing to note here is you can see it reaches a limit because you see the line flattens out. Can you see that? Yeah.
Yes, yes.
So it starts like a heartbeat, something going up and down, and then flattens. And you had some interesting observations. Depending on how you seed the numbers, this spike will change. Okay. And I don't have the time now. I could have shown you 2, 3 different ratio sequences and compared these graphs. It's very interesting. So I will kind of leave it here. Okay. So this is very interesting. So you see the power of Excel now, especially when you're doing sequences. Okay. If you're exploring sequences, Excel is wonderful. Or you want to generate patterns. Okay. All right. So I will stop here and go back to the presentation. So this you saw the power of the spreadsheet. And I'm just stopping here. Just quick thing I wanted to show you. So this is the Fibonacci sequence with the same numbers. If you can see 1, 1, 2. And if you remember the Excel sheet, I will just quickly show you this. You can also make the spiral. Okay. So if you remember, we started with 1, 1, which gave us a 2. So if I make this as, let's say this, just look at the small square. Okay. So this as my radius, like my compass point here, I can make this semicircle. Then with the same compass point, I make this semicircle. Okay. Then I look at the square, which is, so 1 plus 1 is 2. So I got a bigger square 2. Okay. And then with this as the center, I make I'm poor at this next semicircle. Then this as the center of the compass, I make this radius, this semicircle. And with this corner, now you can see 3 plus 2 is 5. So I make a square with 5 here. Sorry, I'm with a mouse. Okay. And then with this corner as your center, I can make this semicircle. Okay. So you get this spiral, which you see in Nautilus shells and stuff, which actually comes from. And the ratio of these rectangles is the golden ratio. So you see both the things working. You can see the Fibonacci sequence here. You can also see the golden ratio. Okay, so let's move on. Okay, now what other things you can do with Excel spreadsheet are, if you are aware of the Buffon's needle experiment, which leads to the value of pi. Okay, this you can do. You can do the Monty Hall problem, the probability one, and also you can do the birthday paradox. That means, well, if I ask you a question, that what
is the probability that we share the same birthday, something like that, right?
Yeah, that's correct. Yeah, so normally the intuition is people would say we need 366 days. Okay, so at least one birthday, but that's not. The thing is, if you have 50 birthdays, 50 different people, then one birthday has to be the same. Okay, so you can show this also with Excel. I mean, I don't have the time, otherwise I would have shown you. So I've done all these 3 with Excel spreadsheets.
Could you please share that in the, like, you can email it to me? How did you do it?
Yes, I will send you the everything. I'll send it to you later. Okay. Okay. So,
I mean, how did you use Excel to make the birthday paradox?
So it's a bit of, it's a bit of programming, but it's very basic. It's not rocket science. You should just know commands, some like COUNTIF and stuff like that, and it's easy. Okay. So all right, let's move on. So this is as far as Excel is concerned. Now let's come to using Desmos sorry, GeoGebra. I use GeoGebra for this. So let's suppose we are doing the derivatives of some function. Okay. Now, of course, students can find the derivative from first principle, which is very algebraic. Okay. But suppose I want to show a visual of this.
Yeah.
So how would this look like? And I want a dynamic sketch. Okay. So this is one example I'm giving you of a dynamic sketch now. So let me just open my GeoGebra file.
Does one need to have a GeoGebra account, or like is it?
Yeah, you need to have a It's easy. It's a free account. Okay, I hope you can see my GeoGebra screen now. Can you see this?
Yes.
Yeah. All right. So here I will, I have made this function. So I will just change. On the top, you see fx. This is e to the power x. I don't want to use that now. I will use sin x.
Okay.
So I use the sine function. Now, just a quick question. If you recall, what is the derivative of sin x?
It's cos x.
It's cos x, right? So the students, you can do by first principles and stuff and all that. But here, I'm showing you the picture of it now.
Sorry, what did you say?
So I'm going to show you a visual gradient function. Okay. So the concept is clear. So right now on your screen, you see the green function, which is the sine function, right?
Yes, yes.
Okay. Now I have made a tangent line. You can see over there. And the tangent kind of looks sort of horizontal. So the slope is 0. So you can see a red dot on top. So what we are going to do when I move these tangents, okay, every time the slope of the tangent will also be plotted on this graph. Is that okay? So for instance, right now, I'll just move it a little. This is like sort of horizontal, right? Tangent. Is that okay? So
yes, it's parallel and horizontal.
Yeah, parallel. So the slope of this tangent will be 0, right? So the red point, you see the dot over there is on 0, right? Horizontally, I mean, okay. So the y value is 0, right?
But why
now
do they move simultaneously?
Yeah, so I will move it now. So I will keep moving the tangent now like this. Can you see? And it's still plotting all the slope points. Now, right now I'm at 45 degrees. So, you know, tan 45 is 1. So, so the red point plotted is at 1. Because that is the slope of this tangent line, which is moving on the green sine function. Okay, so I will now move it quickly all across. Okay, here we go. So I'm moving the tangent line, and you can see the slope at every point is being plotted. I'm moving back and forth. I can do it 2-3 times. And can you see a red function emerging with all the slopes? And you can see what function that is, right? The red one. So that's the cosine function. This is a very strong visual clarification of this concept that the derivative of sine x is cos x, because I have plotted the slopes on each point of sine x in red. And when I look at all the points, it gives me a new function, which is cosine x.
Does the red curve came out automatically?
No, I have used something called a trace function in GeoGebra. So it's tracing all the slope points of my tangent line. Okay. So let me let me just clear this one spot. Okay, here we go. Let me start from here. Okay. So right now I am at 45 degrees. Okay. So what's the tangent of 45? It's 1, right? So you see the red dot there, and my slope, the tangent line is on the sine curve at 45 degrees, right? Now, obviously, as I move forward, the tan value will drop, right? So you can see the red dots coming down, and now it becomes horizontal. I'll just stop here. When it's horizontal, the slope is 0, right? You agree? So you see the red dot is on the x-axis, which is y is equal to 0. The important thing is it's plotting only the tangent values of the tangent which is moving on the sine function, right? The tangent line is not outside. Okay. You see it's slowly moving. It goes down -1 and it moves up. But the beautiful thing is when I take all these slopes together, you get a new function, right?
But you are actually drawing the graph.
No, I'm
drawing the cosine graph.
I'm not drawing the cosine. I'm just moving the tangent line. Okay. What the GeoGebra is doing, it is plotting the slope of the tangent in red. That's all. That's why you see the dots first. Can you see? It wasn't a function. I'll show you again. If I move it very quickly, you'll see only dots. Can you see this?
Okay.
So I'm not plotting a function. That's the concept. the dots are the slopes of the tangent line. But when I keep doing this, like I'll do 2-3 times, okay, so that I fill it up. That means I will take all the slope points. So it will fill up, but even then you can see the shape emerging, right? And you can see this is the cosine function. So this is, the students will have a better understanding of what a derivative is. Now I'll show you another interesting function which students do, which is, what's the derivative of EX?
It's the same, e to the power x.
It's the same. So let's see what happens here. Let me clear this up.
This is not possible in Desmos.
It is possible. I'm not sure. I used this more. 1 minute. Let me just refresh. I actually used GeoGebra much more before Desmos came in. You know, GeoGebra predates Desmos. So yeah, that's why. But I'm sure it would be having, Desmos would also be having this function. It is called a tracing function. Okay. Now let me show you with the EX. Okay. Now you see the tangent line there, and now I will start moving, and it'll plot all the slopes in red. Okay. And this is really interesting. Okay. Can you see where the red line is?
The red dots.
It's on the function itself, right?
Yes, because the same.
It's the same. So therefore the derivative of EX is EX. So do you see
But
the visual?
at which point are you tracing? Where is scrolling up and scrolling down? Where should I hold the mouse?
I'm just doing it randomly. You can see. Wait, I'll show you.
I'm saying, do I have to scroll it on the line of the tangent line?
No. I am just, you see the tangent line there, point G. Can you see that?
Yeah.
Yeah. So at point G, the x coordinate is in the black dot on the x-axis. Can you see? It corresponds to G. Okay.
Yeah.
So I'm just moving that. So I'm just moving the x values. That's it. But the tangent line will keep changing. Can you see it's changing?
Yes.
And automatically the red dots are the slopes which are getting traced. Okay. So I'm
just
actually
scrolling on the x-axis, right?
Yeah, you can see on the x-axis there's a black dot. I'm just moving that forward and backward. Yeah. So so the thing is, the red function is your derivative, and in this case it superimposes on the green one. So that means the derivative of EX is EX. Okay. So this is another beautiful way you can visualize that. You can try many different functions also. Okay. Like,
what about integration? Does it?
Yeah, you can do it. I will show you one on integration later. I have done volumes of revolution. So like, let's take x squared, for instance.
That's a parabola.
Yeah, parabola. So obviously it will be a straight line. So let me just clear this up. The problem with, 1 second, just hang on.
But once I, what is the GeoGebra link? Like, do I have to?
No, this I have, this one I have created. You can see I have made it myself on the side. You can see the author name is mine. Okay. So
can you please share this?
I can share it with you. I'll send
the
a link
to you.
Yeah, no problem. Now let's look at x squared. Okay. So here again, I'm going to do the same thing. There is a tangent line at G. And when I move, it will plot.
There will be a straight line 2x.
2x. So you will see that. So let's move this. Hang on. Okay. Come on, move. Wait. Okay. For some reason, it's just okay. Wait. Let me try again. Okay. There you go. So I'm just moving that tangent line back and forth. And can you see the red line, which is a straight one?
Yeah.
So that's your derivative function, which is 2x, as you rightly said. So this is, I think, a very nice and a powerful visual for understanding derivatives. All right, so let me move on. I will go back to my PowerPoint. So we saw this visualizing the gradient function, and this is a dynamic function, the sketch, what we saw. Now let's look at some limit ideas. Okay. Now this is an applet which was created by someone else, but I just love it, this one, just to give you an intuition of limit using visualization. So let me share this screen, different one. Just a moment. Yeah, here we go. So can you see intuitive notion of a limit screen on your?
Where?
Does it say intuitive notion of a limit? Can you see a sketch?
Yes, yes.
So this is also interesting when you're teaching limits. So right now, if you look at the x-axis, we are at the point 1.5. Okay, and some function is given, a complex. You can see floor plus something. I'll show you with different functions also. So suppose I want to know whether the function has a limit at 1.5. Okay, so this is very beautiful. So there is a slider.
What is that floor? What is that floor of x?
It is some complex function the author has made. Floor, I can change that function also, but I'm just showing you since he has made it. I will change it after a little word. We can take any function we want. So let's say it's some function. I don't care. Okay, my idea is the function continuous or does it have a limit at 1.5? Okay, so the idea is like this. 1.5, I'm going to approach from both ends. You can see right now I'm moving this and making it smaller. But you see on the y-axis, you can see a green line. Okay.
Yeah.
It is basically the range for this red domain, which I have. And I'm actually making the domain smaller. Can you see this? So as I make it smaller, the range also becomes smaller. Can you see it becomes a dot now?
Yeah, yeah.
Which means this has a limit. Okay. Now, I mean, at 1.5, there is a limit. Now, suppose I change this 1.5 and I want to ask, is there a limit at 1 here? Okay. Like this. Now, if I approach 1 from the left side and the right side, can you look at the green lines on top?
Yes.
They are not converging. Can you see? They are wide apart. That means this is a discontinuous function, or there is a discontinuity at 1. So this is a very nice kind of visual. Now let's change this function. I will make a function which I like, which is 1 divided by x minus 1. Okay. So let's see this function here. So can you see this function? I will
hyperbola.
Yeah, it's a hyperbola. Now my question is this function, does it have a limit at 1? Okay. So when I move this slider, as I'm coming closer to 1, you can see the green lines are moving further away. Can you see?
So it's divergent.
It's a divergent and there's no limit. That's the reason. Can you see? And on the opposite side, if I start moving away, you can see that there is a asymptote. I mean, it's not a good idea to show, but I'm just showing the green lines are approaching towards each other. Can you see? Yeah. But the important thing is of the limit. So as far as limit is concerned, as I move towards the point C, which is 1, the range, the green lines are disappearing. They are moving away. So it doesn't have a limit at.
But where are you scrolling it on? Is it on the line?
On the, no. I am on the left side. If you can see, there's a small delta which says 0.53.
Yes.
So I'm making that delta smaller like this. Can you see? Now the red one is becoming small. The domain is becoming smaller. And if I move
as
to
the
the
domain becomes smaller, why do the green lines disappear?
Yeah, because for each point, if you see the corresponding, like let's look at right now on the domain which is on the left side of C. If I hit the below curve, it is at this point, right? The top end of the green. Yeah. So obviously, if I make it smaller, it will go down, further down, right? I'm hitting the curve below because on the left side, the curve is the left side one, which is going down, right?
Yeah.
And on the right side, it is going further up. So the green ones are moving upwards. And on the left side, the green one is moving downwards. So basically, there is no convergence. That's the point.
Okay.
Okay. So this is another good applet. It's again a dynamic sketch.
Are you sharing that applet?
No, I can. Yeah, I'll share that. So and the good thing is you can use many functions. Let's take x square, for example. Okay. Now this is a quadratic. And I want to know, okay, is the function continuous at 1? So you can see I'm moving close towards 1 and the green line is becoming shorter, right? The range is also converging. So that means it is continuous and you can try this at any point. I want to find at 2. Okay. So at the point 2, I move towards 2 from, okay, let me first start from here. So I move towards 2 from the left and the right side. And you can see the green line is converging again, right? As I become very close to 2, it virtually becomes a dot, which means this is continuous and there is a limit. And the limit is 4. You can see that. So this is really beautiful. You can try cube, any like cubic, it's up to you. You can try for a cubic. Let's say I want to know if the cubic function is continuous at 1. Okay, let me just zoom out so I get 1 here. Okay. The same thing. You can say, you can start from here, look at the domain, and I make the domain smaller, smaller, smaller. I'm approaching 1 from both sides. My y values are also approaching 1 from top and bottom. Okay, so the limit is 1. So I hope you like this. Okay. And let me get back to the presentation. All right. So this was visualizing the intuitive way of a notion of a limit. Now let's look at some solids of revolution. Okay. This is again a GeoGebra applet. Let me just open this. So here we go. I hope you can see this. Now, you know, we teach this in grade 11 and 12, solids of revolution. So here, the good thing about this again is a dynamic sketch. I will take the function, an easy function like x, y equals to x. Okay. So it is this straight line. Domain, it's up to you. The one I've used is 1 to 9. Now, the good thing about this is you are basically showing the idea of a solid of revolution. And let me show you, there are some sliders here. You can see on the right side the solid, right? So I can show you this. These are the same picture which is on the left. Do you see this?
Yeah.
Yeah. And where I can make, now imagine if you're rotating all these on the left, slowly I can do it like there. Can you see the rings forming? And they become the solid. Yes. Now, right now, it is not a perfect solid in the sense it's not a smooth one because you can see these small triangles on top of the line, right? That means we must increase the number of discs. That's the idea of integration. So here I go. I click the bottom bar, make it 5, 6, 7. Now you can see as I'm increasing, the small triangles which are above the line are becoming smaller. Okay. And as I tend to infinity, like I'll make it bigger. Can you see you're getting a perfect solid now on the right side?
Okay.
Okay. So this the same idea you can use for integration. Also, I have some.
So the triangle disappears as you
exactly. Yeah. Exactly. So it's a truncated cone. If you can see, yeah. I started with let's say I start with 2 discs. Okay. This is not a good one.
Started with cylinder and then.
Yeah, it's actually a cylinder. You're right. If you are at 1, it's a cylinder. Then I make it better, like 1, 2, 3, 4, and you can see on the, and every time you can show this picture by moving the other slider. So the concept is clear. You see the same triangles, these bars are there. And you can also move this, by the way. So let me.
That means if they integrate the function x and was the limit, increase the limit.
Yeah, that's right. So when the limit tends to infinity, when the n tends to infinity, it becomes a perfect solid. Okay. So now, so here are the rings again, and you can move this around. That's the beauty, you know. They can visualize this. Can you see I'm moving this cone?
Oh.
Okay, rather a truncated cone because it doesn't start from 0. So you can actually play around with this. You can look at it from different angles, and you can always see those same the small rectangular strips which you see on the left. Okay, you can decrease and see also. This is just a rectangle. So obviously, like you said, you got a cylinder from this. When I made it 2 or maybe 8, you got these rings, but these are still not perfect because they're above the line. That's the whole idea. Okay. So how do I reduce these small triangles which are above the line? By making the number of discs more. And you see they start disappearing till they become perfect. Okay. This is n is 50. You can make it 100 also.
What is the n here, by the way?
N I have taken as 50, but you can take it 100 also. This is just for illustration. Okay. So there, I will show you another view of this. So this is a solid.
And shall we keep a equals to 1 and b equals to 9 always?
It's up to you. You can make a 0 also. Suppose I make this 0, you will get a cone. If you see it's a cone now, I've made a 0. Okay. Yeah, I can make a 8 or it's up to you. You can just play with it. You can make it a smaller one. there. So this is a perfect cone. Earlier it was I was using a truncated because I was using 1 to something. Okay.
Yeah.
Yeah, and here again,
That's why I was wondering, if you take 0, will it be a
yeah, 0 is a perfect cone. If I start from 1, then it's a truncated cone. Okay. So this is a cylinder from 0, if you can see. I'll just move this around.
But how does it, if the students ask me, how do I relate it to its integration?
No, the integration thing is when you are taking a cone, for instance, okay, the idea is cone, the function is y is equal to x, right?
Yes.
So when you do integration, you know the idea that these are approximations, right? I've made these 3 rectangles, but the area under the curve of this triangle will be a little more, right? Because of those 3 triangles on top, right?
Yeah.
So what do? I make more rectangles. I make 4 rectangles. Now there are 4 triangles with a lesser area. I go on increasing. Can you see the triangles? So I'm basically minimizing the area above that line, y equal to x. And at the same time, when I spin this, if I spin this each rectangular strip, okay, here, I'll show here. On the left side, you can see, if I spin it, I will get discs, right? Can you see the discs coming? Yeah. So each disc will have slightly little more volume, right, than the actual volume because of these small triangles which are above y equal to x. So our whole idea is to make this 0, okay, which I can only do by increasing, making the rectangular strip smaller and smaller. So as n tends to infinity, the area on top will tend to 0. And therefore you will get a solid of revolution. And each disk, okay, you tell me what's the area of each disk, pi r square, right? But yeah, you see there are many radius, there are many radii, right? Each strip has a different radius. So that's why you get that formula. You know, the pi, you pull it outside, and r is y basically. That means f of x, right? Yeah. So pi integration of f of x squared. That means you're integrating all the disks, okay, all the volumes. Yeah. So this is a very nice visual way of explaining solids of revolution, and also integrate. I have integration. For this presentation I didn't bring it, but the same on the left side idea is the one like this one for integration. How to make these rectangular strips smaller and smaller, okay, till I get the area under the area under the line.
Coming. The left bar chart coming on the disk, isn't it?
Yeah, that's correct. So you're right. But here only the difference is we are rotating the bar charts, okay? But in integration, if you look at this, okay, let me show you a different view if I can. Yeah. Integration is simply finding this area under the line, right? The area of this triangle. But right now the area is a little more because of the small triangles on top of the line. Okay. Yeah. And the only way to get rid of them is to increase the number of rectangles. Can you see like this? So this area is the integrated area. It's the area under this curve between this domain 0 and 7. Yeah. But the spin is when I rotate it, then it's this left side, if you can see now, it becomes like this. Okay. So you get the cone. If it's 2 dimensions, it's just the area of that triangle.
That means, are you rotating the straight line? Y equals x.
We are rotating. No. We are rotating every bar chart. Okay. Every. Okay. Let me just make this smaller. Suppose there were three bar charts like this. Okay.
Okay.
Okay. Now, if I spin each one of them over the x-axis, okay. So you look at the left side, what happens? Can you see 3 discs will appear? Can you visualize that?
Yeah.
Yeah. That's the idea. So each of these rectangles is spinning on the x-axis. So it creates a disc. Yeah. And when I increase these number of discs up to, I mean, right now it's 50, but up to infinity, you will get a perfect solid, a perfect cone rather. Yeah.
Okay.
Okay. So these are really good, dynamic sketches one should use in calculus. All right. So let me get back to the presentation. All right. Now I'll show you something which is you must have seen when you teach 3D geometry. Students have difficulty visualizing the the longest diagonal, right? From one corner to the bottom corner to the top corner and stuff, right? Or surface area and things like that. So if you have a phone now, you can do it right now. I can teach you, or I will show you a small video I've made. So there is an app in GeoGebra called 3D Geometry.
Shall I take my phone?
Yeah, you have your phone. Can you go to the, yours is an Android. Which one is it?
Yes, Android, Samsung Android.
Okay, so in Android, you go to your store, Google Play, and just click on, I will just show you. Just give me a second. Can you just type 3D calculator? You will see a 3D calculator. You will see a pyramid. It's a GeoGebra app.
3D calculator, shall I type?
Yeah, just type 3D calculator and you should see a purple pyramid. I'm going to play this, so just pay attention. I'll play it again if you wish. So just have a look. This is my phone screenshot. I mean, I took a screencast of my phone. So I'm just going to play it now. Good morning, everyone. This is Shiv here, and I will show you how to use the GeoGebra 3D.
I can see. I cannot see.
Reality. You can.
You can only see the desktop or your phone of your phone.
Hang on. No, on the desktop, do you see a video screen now? My phone or something?
Yeah, it's just this, just the desktop screen.
Yeah, but do you see like on the in the PowerPoint there is a this thing? What do you call it? My phone screen. Do you see that?
Yes, yes.
Yeah. So I'm playing this. So this is a video I made. So just watch this. Good morning, everyone. This is Shiv here, and I will show you how to use the GeoGebra 3D augmented reality. So this is how you go. You go to the app first, which is, and here you click open. So from here, I'll choose surface area. And now you click the AR button and just choose any surface. So I've chosen this surface and just tap on it. And there you get this cuboid. Now I'm moving around with my phone and looking at this cuboid from different angles. So this really helps to visualize what these 3D objects look like. So
can you do that again? I missed it. Like, can you go back?
Should I play it? And I'll pause it. You just tell me pause. I'll pause there. Okay. Okay. So first you open your phone, and of course you know where your 3D augmented reality. So this is how you go. You go to the app first, which is this one, 3D calculator. Can you see that? Oh, sorry. Just give me a second. Just play it. Yeah. Good morning, everyone. This is Shiv here, and I will show you augmented reality. This is how you go. You go to the app first, which is. Oops. Okay, I'll play the full thing. You just have a look. It's very easy. Okay. Good morning, everyone.
I'm on that page. I'm on the GeoGebra page, but where should I go now?
Okay. GeoGebra 3D augmented reality.
Tools?
So this is how you go. No, open. Do you see there is an open button on the left side? Okay, I'll just show you on this. You can see on this video. Yeah, here on your screen. Do you see this? When you open on your phone, do you see this on your phone?
I can't see the lower part of that, you know, that box of ABC.
Don't worry about the lower part. On the left corner, do you see 3 lines on the left top? 3 lines.
Yeah, I can see X, Y, and Z axis, 3 axis.
No, also 3 small lines. Can you see left top corner, 3 small lines on my screen?
Yes, yes, I can see.
Can you click there and click open there?
Yes, I opened it.
So wait, yeah. So let's just watch now.
Click open. It says allow or deny.
Allow. You say allow because it'll ask your camera. That's why.
And then which one shall I choose? Surface area.
Can you choose surface area now? Yeah. So from here, I'll choose surface area. And it'll load. And then what you do. And now you click the AR. There is an AR button on your screen. You will see AR. Can you click that?
No, I can move that object, but where is that AR?
No, AR is on your screen. You should see AR. Like I'll show you again. After you choose the surface area, you see this AR thing at the right corner, bottom, AR.
No, no.
It should come on your phone.
I can see tools at the right and algebra on my left. And the
bottom,
three
AR
lines.
Yeah, three lines are there.
Also.
You're right. You have the toolbar, and at the right bottom you have AR. Can you see on my screen AR written?
Yes, I can see AR on your screen, but where is that?
Not on your phone. Okay, so maybe you have to give some permission, but it's easy. So I'll just explain that. You can try again. Then after you click AR, this is what happens. You have to choose any surface area. Like I chose my table. Okay, sorry, this keeps. Just a minute. Okay, I'll just fast forward.
Good morning, everyone.
So what I did was
choose surface area.
Surface, this you chose. Okay, then you will see it will load. Then you will see.
Now you click the AR button.
Now, after clicking the AR button, just point your camera at any surface, like table or something. Okay, like
Just
this.
choose any surface.
I chose my table like this. You'll see that,
tap on it.
and just tap there.
And there you get this cuboid. Now I'm moving around with my phone and looking at this cuboid from different angles.
So you just need to find the AR button. You know, if you get it, then it's very easy. And this is really now these sketches you open. You can make your own sketches. Like I have made some on my own for the diagonal in a cuboid. Okay, so a student can actually understand how to apply the Pythagoras theorem there. You know, for visualization.
This really helps to visualize what these 3D objects look like.
So anyway, I hope, just try, I'm sure you will get it. Now, this is something interesting. I think we are towards the end now. This is with Desmos, and Desmos has some set of lessons. Okay, they're really interesting for developing the concepts, and it follows a very constructivist approach. So I'll just most probably end with this. So let me show you this feature. So this activity, this is called marble slides. This is basically about straight lines. Okay, so I'll show you how this works, and you can use it for your whole class. So these are the screens. Now I will show you a student preview. I'll tell you what a student would do once you share the link with him. Okay, so it says student preview here. So can you look at the left side? It says, here's the goal. Get all the stars, get to know the line.
Shall I type the let's marble site?
I can send you this link. Wait, no, just a minute. Maybe you can work along with me. Hang on. I will paste the link in your chat box. Okay, just give me 1 minute. So, so let me just take a few slides with you. Maybe you can answer looking at the screen. Okay, and then you can try on your own. I've sent you the link. So if you look on the left side, it says, I have to get all these stars. There are 4 yellow stars, right? It says launch the button. Let's see what happens when I press launch. And there is a ball on top. You see the purple one?
Here is the goal. Get all the stars.
Yeah, so let me launch. So once I hit launch, this is what happens. Can you see? It hits all the stars, right? So this explains launch button. The launch, can you see on the right top, launch?
Yes, I clicked it. Yes, all the balls are going down.
Correct. So this is just to get you familiarized with what launch means. Okay, now let's go to the next slide on top. Next. Okay. So
yes, I can see straight line.
Yeah, there is a straight line. Now this is very interesting. It says change one number in this equation so that, okay, let me just launch the ball now. See how the ball goes now. See, it goes like this, correct?
Yes.
How do I change this line or some number in this line so that I can get all the stars? Can you suggest something?
Sorry, say that again.
So you have the equation y equals to half x plus 1, right?
Yes.
Which number can I change a little so that I can get all these 4 stars, you know? So for instance,
if you change the gradient, obviously it will change.
Gradient also, I can also do a translation of the line, right? I can move it up and down also.
Yes, you can change the constant number, C.
So maybe let's take -1. Let's check. I don't know. Is this better? No. Maybe I should take -2. This looks good, right?
You want to touch the star.
Yeah, we need all the stars after I drop the ball, the purple ball. Okay. So, and let's try 3. 3
Yes,
is here.
all
Okay.
the stars gone. If I give it to -2, all the stars gone.
So that's what we have to do. You have to get all this. So now if I launch the ball now, okay, you will see it, you get all the stars, right?
If you do what?
Launch. If you launch now, you will see you will get all the stars. The ball will fall and you will get all the stars, right?
Yeah.
So this is, see what the student is learning now, that which number affects the line in which way. You know, it's a very nice approach.
Yeah, to teach the coordinate geometry.
Yeah, so what you are doing is, like, when I change the constant, it moves the line horizontally. Okay, now let's go to the next one. Okay, I will just skip this. This is some instructions. Okay, let's look at this question. There is a line given, 4x plus 3. I need to get all those 4 yellow stars. Now which number should I change 4 or should I change 3? And you can play around with it. Actually, you can change and see how it looks. Okay. So let's make
slide number 3.
Slide number 4. It says fix it to.
Yes.
Okay.
What should
So
I do
here,
now?
yeah. So here now you see y is equal to 4x plus 3, right? So the student has to make some changes to numbers so that he gets all the 4 stars.
Okay.
So this is also example of slight kind of a gamification and also constructivist approach. Okay. So I think I will change.
Now I have to increase the gradient.
Increase. So what number you want to make, for example?
If I make 10, it will be too much steeper.
10 will be, you won't get the stars, right? At 10. Yeah.
If it is 1x, then it's closer.
But that means I need to reduce more. So maybe take half x then, right?
Yeah. So what was it previously?
I think it was 4x, right?
Yes, half x actually it does give.
Yeah. So now let's launch. Yeah. So let's
launch
launch the ball and check. Yeah. So can you see it's success, right? So what
did you put 5x plus 3?
No, 0.5x plus 3. Yeah.
Okay.
So here you learn how the slope changes when you are changing that value. You saw? Yeah.
Yes.
So this is again, it's a very good way to concretize these concepts.
That means when we reduce the gradient,
yeah,
the line gets less steeper, right?
Less steeper, exactly. That's what we did, right? Because see, when we tried 1, if you can see my screen, this was 1x, right? Actually, originally they had given 4x. This is the original question. Okay. So the student could have thought, okay, if I change 3, maybe I will get, like, let's say -3. Okay. But nothing, still he sees you can come closer to the stars, but you can't hit all the stars. So let's say -5 or -7 or -9, or let's say -10. Okay, let's take -12. Okay, now if I launch the ball, nothing happens. The ball won't reach there, right? So if you launch the ball, now it won't. Obviously, it will drop perpendicular because there is no line there, right?
Right.
So so that means changing this doesn't matter. I must change the slope now. So then he will play with the slope. He might make it 3x or 2x or even 1x like we tried, but 1x also is not good enough. You see, I have to make
then you have to reduce.
So he has to think of decimals then, like half x, like
what if it is 0.6x?
Yeah, he can try. So let's say 0.6x. It's like,
that's too much.
Let's launch and try. So you see, you are missing out on the star. That means I must increase the slope. So, or rather decrease. Okay.
Yeah, decrease. Oh, now is what happened?
No, it actually it was +4. That's the mistake. Yeah. I changed the original. I don't remember what was it. Was it +4 or 1? I don't remember.
Was it 4x plus 3 something? Okay.
It was 4x plus something. I don't remember what was it. Plus what?
I think 4x plus 3. Can you try?
Yeah, that's right. So now it's correct. Yeah, now if you launch, obviously it'll hit you. You can collect all the stars. So this is beautiful, right? So just
So
by
did you make it, or was it there already in Dustmos?
no, this was already created by someone. It's a complete lesson. You can see there are 24 slides. Can you see on top? 4 of 24. Yeah.
Okay.
So these are so this is again use of technology, but created by someone, some experts. Okay. And this is really kind of I found it very useful, for students, and their motivation is very high, when they do these.
Will you use it in DP class or?
No. This I would use it in grade, let's say 8, okay, 8 or 9 when I'm starting straight lines. Y is equal to mx plus c.
Okay, that's great.
DP, no, not that much, unless there is some student who's very weak. Only then.
No, because I can see once I go forward with the slides, I can see there is some inequality. There is some x is less than 2. If you go to slide number 8,
okay,
go to slide number 8, please. It says y equals to minus 0.14x
1 minute
plus 3 bracket x is less than 2.
No, that's just the domain given. X less than 2 is just the domain. That's all.
Yeah, what I'm saying, grade 8 students may not be aware of what the what.
Yeah, you can just tell them. You can tell them you can only choose x values which are less than 2. That's it. That's all. Yeah.
Okay.
Yeah.
X values, but you mean that like not the number 0.14? That's the coefficient, right?
Yeah, that's right. That's the slope. Actually, it's a negative slope. Yeah.
Negative slope. Yeah.
So
if we change that to 2, okay, right.
Yeah. It's just saying if we changed 0. If you change the slope to 2, for example, it says what would happen to the graph. So let's put 2 here and see.
Minus 2x.
Minus 2x. Okay. So it looks like this.
But it cannot be minus. It has to be less than 2. Oh yes, minus 2 is less than 2.
No, minus 2 is less than 2. Yeah. So everything less than 2. Okay. So the line looks like this. Yeah.
It shows a broken line.
Broken line is the original one. Okay.
Okay.
So
that it has gone further right.
Right. It has moved upwards, if you see. Yeah.
Upwards. Yeah.
Yeah. So exactly. So these are, so this, you can do this for grade 8, 9th also. It's up to you, depending on the level of your students.
Right.
So
right.
These are really, really interesting and good use of technology, I feel. Yeah.
Definitely.
Yeah. So I think I'll wrap up now. Okay. Let me just go back to the slides.
But please, share those previous.
Yeah. Sure.
Desmos, I know much more or less, but the other ones like GeoGebra and the other one, like
sure.
Applet one, I don't have any idea.
Okay. So I will just end with this.
I'd like to explore more on this, and if I have any question, I'll get back to you.
Right. And so I will just end with one slide since we are out of time. So let me share. So I will just end with this slide. We don't have time. So I would have taken gamification also. So basically, this is the summary, what we saw. We saw visualization. You saw experimentation in the spreadsheet we did. You can see how it sustains students' interest. The teacher is a facilitator. Okay, and trivialization of calculations, which is important, that again, you saw in the spreadsheet how it populates all these columns automatically based on some formula. Okay, so I'll kind of end it with this. And I just hope you use more and more of these technologies in a judicious manner.